Bismillahirrahmanirrahim. Salatu wassalamu ala Rasulillah. So, assalamu alaikum. So today we will solve recitation problem for chapter 28. I was very happy to notice that some students, I hope most of you have already solved this recitation problem. I talked to Abdul Malik, so I'm very proud of you guys, those who solved it. So those who did not solve it, please solve it, and this is the recording, okay? Now, let's start by the first problem. We already solved this in class, okay? We solved it today. But let me just remind you what I said. Let's read the problem. We have a rectangular conducting current carrying loop, and it's placed in the figure as shown below. So here you see the current which is going across my rectangular loop. The current is just I is equal to 15. Okay, 15 amp. And this rectangular loop is in a uniform magnetic field, and B is along X direction. Okay, B is uniform. Okay, it's uniform magnetic field, and the magnitude of B is 0.48 Tesla. So B itself is 0.48 Tesla along the direction of I hat. Now the question is, what is the torque on the loop? Okay, and we already discussed this in class. So as we said, torque on a current carrying loop is equal to mu, which is the magnetic dipole moment, cos B, the magnetic field. So this is the torque on my loop. So let's calculate the magnetic dipole moment. As you know, the magnetic dipole moment, mu, is number of turns multiplied by the current, multiplied by the area of the loop, multiplied by n hat. N hat is a unit vector, unit vector normal to the area. Okay, so it's a normal vector. So n, let me write it here. As we said, this is a normal vector. Of course, the normal vector is a unit vector. That's why I put n hat. It's a unit vector normal to the area of the loop. Now, there are two ways to be normal: normal inward or normal outward. Okay, so that will be determined by the right-hand rule. Okay, as I said in class, if I'm rotating this way, if the current is going in this direction, so if you use the right-hand rule, it gives you a normal vector which is in which direction? Inward. Okay, so n is inward, so that means mu is inward. Okay, of course, if the current is going counterclockwise, so you can use, so your normal vector will be in which direction? Outward, of course. So your magnetic dipole moment will be outward. Okay, good. Now here, how is our normal vector? Of course, I'm rotating in this direction. So you see current here. Current is moving in this direction in the loop. So if you use your right-hand rule, the normal vector will be like this. Okay, good. So let's come back to our torque. So our torque will be, as we said, n number of turns, I current multiplied by area multiplied by normal vector cos B. Okay, good. Now let's write our normal vector here. You see, normal vector, it has three components: along X, along Y, and along Z. I hope you see that along Y, the normal vector is 0. Along X, what's the normal vector? I mean, the component of the normal vector along X and X. It will be 1. This is the magnitude. Cosine, which angle? So you see here, My normal vector, I can put it here if you want. So this is going here. So the normal vector. So I'm just displacing this vector here. I put it here. Okay. So what is the normal vector? So if I put it, I can put it here as well if I want. So all these vectors are the same. Okay. So it will be cosine. You see here, it will be minus 30 degree because I'm rotating in this direction minus 30 degree, and then I'm adding 90 degree here. Okay, because the normal vector is 90 degree here. You see, this is 90 degree. So plus 90 degree. So nx is just cosine 60 degree. Ny is 0 and nz is what? Is 1. Now nz here is negative because if I project it along z here, it will be negative. Okay, it's z is positive z here, is negative z is there. So if this is 60, of course, this is my nx. So let me take my, okay, as a color here. So as I discussed, this is nx. This is 60 degree, and this is ny. Nz, sorry. Ny is 0. So this is nz. Okay, and z is negative, so I put minus sine 60 degree. Okay, so let me come back to my talk. It will be n, number of turn, I, a. Now n, I can write it. I will have cosine 60 degree I hat minus sine 60 degree k hat. And then this cross b, which is 0.48 I hat. So I'll have nia, I hat cos I hat is 0. Now k hat cos j hat, that's I hat. That's basically, let me write it down. Okay. So as I said here, you will have 0. I'm taking this, cos this, it's 0. Now second thing, I have this, cos here. So this will give me minus 60 degree, sine 60 degree, times 0.48. Now k hat cos I hat, this gives me j hat. So I put the numbers. Here I will have 1, number of turn is 1, the current is 15, the area is 8, 10 to the power minus 2, this is 8 centimeters, and then the width is 6 centimeters, and then I multiply by 0.48, then I multiply by minus sine 60. I already discussed this in class, okay, j hat. And this will give me minus 0.03 j hat Newton meter. Okay, so the only difficulty here is to locate the normal vector. And the direction of the normal vector gives me the direction of my magnetic dipole moment. Okay, so this angle was the only difficulty here. Okay, and to know that, you know, my nx is cosine 60, my ny is 0, and my nz is minus sine 60. And then I apply my cross product rule, and then I get my torque. Okay, we already discussed this as well. So I can skip it. The solution is given. Okay, this is very important. So we discussed this in class, and I solved this in class. Okay, so I will skip it. I discussed this as well in class, and we solve it in class. Okay. So I will skip it as well. We discussed this also in class. Let's discuss it again. So I have a long wire carrying a 6 amperes current. So reverse its direction by means of 2 right angles as shown in the figure below. So you see here, I'm going in this direction. This is the direction of the current. And here the direction of the current is downward. And here the direction of the current is leftward. So the current was coming rightward, then downward, then leftward. Now in this region here, I put a magnetic field which has a certain magnitude. So the magnetic field is pointing outside towards you. As you see, the arrow is pointing towards you. If it was inside, you will see I will put it like this. Okay. This is inside, inward. Okay. When I put the magnetic field like this is outward, of course, you know this already, or outside, pointing towards you. Okay? So here the magnetic field is pointing towards you. And the question is very simple. If I give you this diameter here, and I give you, of course, this distance here, the question is very simple. To calculate the net magnetic force on the wire. So as you know, if I have a current carrying wire, inside the magnetic field, there is a magnetic force. Magnetic force, as we discussed, is IL plus B. Okay. Now that means here I have some magnetic force. Let me write it in red. So here I have some magnetic force. What is the direction of the magnetic force here? Can you tell me? So you use the right-hand rule, okay? As we discuss in class. So what should be the direction of the magnetic force here? So it's pointing downward here, okay? Now what's the direction of the magnetic force here? It's pointing leftward. And what's the direction of the magnetic force here? It's pointing upward. So this magnetic force here and this magnetic force are equal and opposite to each other, so they will cancel. So the only net magnetic force is this magnetic force, which is due to this portion of my wire here, this portion of the wire. Okay, so that magnetic force, so this on top and bottom, they will cancel. So I just have the magnetic force pointing to the left using the right-hand rule. So that magnetic force has a magnitude FB, which is ILB. Now L being, of course, this length here. Okay. Now sign between L and B, the sign between them is 90 degrees. So the sign is just 1. It's just ILB. So I know everything. I know I, 6. I know L, 0.45. I know B, which is 0.7. And I calculate it in Newton. And it gives me, of course, 1.9 Newton. We discuss this in class, okay? Always look at the direction of the magnetic field, right-hand rule. Okay. Good. We look at the next question, which is similar, and we already solved it in class as well. So I can skip it. I will solve another problem like this. We already solved this problem in class. Again, in the solution here, you see here there is a mistake here. Okay, so this should be FB2 and this should be FB1. Right, you know, to be consistent between this notation and this notation. Okay, good. Now let's solve this problem here. We have a coil, as described in this figure, parallel to the XZ plane, and it carries a current. So this is my current, 2 amp, in the direction indicated. So this direction. So the current is going in this direction. So first I can determine where is the normal vector. If the current is going in this direction, what do you think? The normal vector is pointing down. Okay. So the normal vector, which is the unit vector, is pointing down. So the normal vector here is just minus j hat. Okay. N hat, which is my normal vector, is pointing downward, minus j hat. So you know that my magnetic moment, my magnetic dipole moment will point downward. So what is the magnetic dipole moment? Is just N, the number of turns, I, the current, multiplied by the area of the loop, multiplied by N. So here, you see here, I told you this here, that it has 3 turns, so the number of turns is equal to 3. The current is 2 amp. Area is given here, 5 10 to the power minus 4. Of course, the units are amperes, meter square, and N hat is just minus J hat. So this is my magnetic dipole moment. Okay, it's along J hat and it has this magnitude. It's along minus J hat and it has this magnitude. Now, as I said, here's a coil lies in a uniform magnetic field given by this. So I give you the magnetic field B, just 2 millitesla. Millitesla is 10 to the power minus 3 Tesla along I hat. Okay, so let me write it this way. Plus minus 3, 10 to the power minus 3 millitesla, 10 to the power minus 3 Tesla along J hat. Okay. So I put the millitesla in Tesla, that's why I'm putting 10 to the power minus 3 here. Now the question is very simple. What is the orientation energy of the coil? Okay. You know that the energy, orientation energy is the potential energy actually. So, of the magnetic dipole moment. So it's just minus mu dot B. It's a dot product, okay? So I know minus mu will give me minus, so I can calculate this, minus 30 10 to the power minus 4. So this is it. It's minus J hat. So this minus and this minus gives me plus. Then I take a dot product with the magnetic field. So magnetic field is 2 10 to the power minus 3 I hat minus 3 10 to the power minus 3 J hat. So let's distribute. Of course, J hat dot I hat is 0. J hat dot J hat is 1. So I will have what? I will have plus 30 10 to the power minus 4 times minus 3 10 to the power minus 3. Okay. And it will be joule. So this gives me minus 9 10 to the power minus 6 joule, which is minus 9 microjoule. This is my answer, of course, and you know it. Okay. Good. Now, if I ask you to calculate the torque, what is a torque acting on this loop? You know that the torque will be mu cross B. Okay. So the potential energy, orientation potential energy is mu dot B. It's a dot product. Okay. In other words, it's just mu, magnitude of mu, magnitude of B, cosine the angle between mu and B. Okay. Or in other words, it's just minus mu x bx minus mu y by minus mu z bz. Okay, there are many ways to express the dot product, and you know geometrically what it means. So here, if I ask you to calculate the torque, what do? You know this, and you know B, and you know how to calculate the torque, a cross product. Okay. So you remember, you say I hat, J hat, and K hat, and then you put the component of the torque here. So of course, along X, it's 0. I mean, the component of the dipole moment. Okay. So along X, it's 0. Along Y, you will have what? Plus 3 10 to the power minus 3. And along J, along Z, which is along K hat, is 0 also. And then the magnetic field is what? Is 2 10 to the power minus 3 along I hat, along j hat is minus 3 10 to the power minus 3, and along k is 0. And you remember how to calculate this determinant, okay? So calculate it and get me the torque, okay? And you know that, of course, what my torque wants to do, it wants to align the normal vector in the direction of the magnetic field. You know that already, as we discussed in class. So you can calculate the torque. Okay, same problem. Get me the torque acting on my coil. Next problem. So here, what do we have? We have a wire bent shown in the figure. It lies in a uniform magnetic field, and I give you the uniform magnetic field. So B is 0 along X, 0 along Y, and 4 Tesla along Z. So each wire section is 2 meters. So you see here, this wire section here, the length is 2 meters. I call it L1. So L1 is equal to L2 is equal to 2 meters, each of them. So, and they make an angle theta, which is 60 degrees with the positive x-axis. So basically this angle here is theta, is 60 degrees, and this angle here is theta, 60 degrees. And the wire carries a current of 2 amps. So here I have a current which is moving in this direction, 2 amps, and the current here is moving up, it's 2 amps. And the question is simple. What is the net magnetic force on the wire? So this is my positive x-axis, this is my positive y-axis. So Z is pointing out of the page towards you, right? So Z is pointing out of the page towards you, positive. Okay, so here I have, let's say, 2 straight wires, okay? So I have here portion 1, and here I have portion 2. Each of them has a length L1 and L2, which is 2 meters. So let me calculate the magnetic force on wire 1. Of course, the magnetic force is just I, L1 plus B. Now, what is L1? L1 is this vector here. Let me take another color here. So this is L1. Okay. This is the length vector L1. So let's get the components of L1. So L1, you see here, is continuing here. Okay. This is L1. So how to get the X component of L1? Of course, the X component of L1 will be magnitude of L1 cosine the angle. And the cosine of the angle is 60 degrees. But don't forget to take a minus sign because L1 is in the 3rd quadrant, okay? So it has a negative X component and a negative Y component, okay? So this is 60. So here I have minus L1 cosine 60 degrees, okay? Let me put it theta, just to put it theta, okay? And L1 along Y is minus L1 sine theta, and L1 along Z is 0. Okay. So let's calculate our FB1. FB1 is a current, so the current is 2. Now I will calculate L1. So L1, which is this, so I know the components, minus 2 cosine theta minus 2 sine theta and 0. Now this cos B, so B is 0, 0, 4. Okay, you know how to calculate. You know how to calculate the cross product between 2 vectors. Okay, you remember you can use a determinant. So L1 cos B, what do? You use a determinant, I hat, J hat, K hat, if you want. Okay. And then here you will have -2 cosine theta. Here you will have -2 sine theta. And here you have 0, and here you have 0, 0, 4. So this is one way to do it. Okay. The other way to do it is to just say that, this is 2, and here you will have -2 cosine theta I hat, -2 sine theta J hat, and then this cos 4K hat. And then you use what you know. You know that I hat cos K hat is minus J hat. Okay. And of course, J hat cos K hat, this gives you I hat. Okay. So if you calculate that here, what do you have? So let me get, this minus here, put it out here. So I will have 2 times -2, so -4 times 4. So this gives me 4. So 16. Okay, so I have -16. And then I have my cosine theta I hat plus sine theta J hat cos K. And then I use this, okay? And of course, this will give me what? -16 cosine theta. So I had cos K hat. This gives me minus J hat. So minus J hat. And J hat cos K hat. This gives me, of course, I hat. Okay? I'm just multiplying here. Then I get this, so I get this. So this gives me, so now I can put cosine theta if I want, So I will have just this plus 16 cosine theta along I hat, along J hat. Sorry, okay, you have be careful, okay? So I'm looking along I hat. What do I have along I hat? So here I will have minus 16 sine theta along I hat. Along J hat, I will have plus 16 cosine theta. And along K hat, I have 0. So this is my vector, FB1. Now let's calculate FB2. FB2 will be I L2 vector cos B. Now what's L2 vector? L2 vector is this vector here. So what are the components of L2? Along X is negative, it's minus L2 cosine theta. So basically this is negative along X. This is my L2X. And along Y, it's plus L2 sine theta. Like in physics 101, and along Z is 0. So I'll have 2. Now L2, I'll have minus 2 cosine theta I hat plus 2 sine theta J hat. And now this cos B. Now B is for K hat. So this gives me what? Let me get, put all the constant out. So I will have 16 minus cosine I hat plus sine theta J hat cos K. Now this I will distribute it inside here. I will have 16 minus cosine I hat cos K hat. This gives me minus J hat, so plus J hat. And then here I will have what? J hat cos K hat. This gives me plus I hat. So sine theta I hat. So FB2, I know it, of course, it's plus 16 sine theta along I hat, and then I have plus 16 cosine theta along j hat, and I have 0 along k hat. Now, let me add them. So the net force is just FB1 plus FB2. And you see, along x, they will cancel. I will have minus 16 sine theta plus 16 cosine sine theta. So this will give me 0 along x. Along y, I will just have 32 cosine theta. And then along z, I have 0. So the net force, F net, as I knew, is just 32 cosine theta j hat. So this gives me 32 cosine theta is 1/2 because theta is 60 degree j hat. So this gives me just 16 Newton along j hat. Okay. So bottom line, you need to know how to calculate the Cos product, either by using this, the determinant, either by using these formulas. Okay. I hat cross j hat gives you k hat, etc., etc. Okay, so you can develop easily without making a mistake. Okay, great. So let me just erase this, and the solution is given here. So here I use this formula, this approach, the second one. Okay, there are many ways to solve the same problem. You do it as quick as possible and without a mistake, of course. Okay, now let's solve this problem here. So I give you a particle and I give you the mass of the particle. This is M. The negative charge, so it has a negative charge. Q is negative. So it's traveling through a region containing a uniform magnetic field, and I give you the uniform magnetic field. I give you the components, 0 along x, 0 along y, and minus 0.12 along k hat, on z. So at a particular instance, the velocity of the particle is given, is equal to v naught. So this I call it v naught. And then it has, v naught multiplied by minus 3i hat plus 4j hat plus 12k hat. And the force on the particle has a magnitude of 2.45 Newton. So determine the magnitude of the charge of the particle. So here I have a charged particle in a magnetic field. The magnetic force, FB, is a Lorentz force, QV cross B. Okay, great. So that means that Q is just FB divided by V cross B. But I want, of course, a magnitude. So I will take magnitude here. So be careful. So here I mean by magnitude. The Q here, the magnitude is this. Okay, and this is the magnitude of the charge. Okay. You don't divide by a vector, but here if I take the magnitude, I can take this. I can take magnitude of the force divided by magnitude of V cross B. So magnitude of the force is given 2.45 Newton. Now I have to get what the magnitude of V cross B. Easy. I gave you V. Okay, what's V? V is V naught minus 3 meter per second along I hat plus 4 meter per second J hat and plus 12. Okay, V naught being 1.05 10 to the power 6. Now I want to take this cross B. And B is 0 along x, 0 along y, and minus 0.12 along z. Okay, so you know everything here. You can get what is the cross product. I know the components of V, and I know the components of B. So what's the cross product? What's the magnitude of the cross product? You can calculate it. Okay. Good. So if you calculate it, what do we find? I'm talking about V cross B. So what do I find is this. Along X, I will have plus 4 times minus 0.12. And then I have 0 here. Along Y, I will have I have 0 first, and then I have minus 3 minus 0.12. And along Z, I will have 0. So V cross B, of course, don't forget the V naught. Okay. So V cross B gives me V naught. So here, I have what? I have 4 times minus 0.12. And here I will have plus 3 times minus 0.12. And then I have 0 here. So this is V cross B. So that means the magnitude of V cross B will be what? Will be V naught square root of 4 square times 3 square. And then I will have outside here 0.12. Okay, so I can calculate what is this magnitude. So I will have 0.12 times 1.05 10 to the power 6 times square root of 25, which is 5. So, and I take it and I plug it here, of course, and then I get my charge. So the charge is just 3.89 10 to the power minus 6 coulomb. Okay. Is it clear? You know the components of V, you know the components of B. You can get what are the component of V cross B using either the determinant or using, the I hat cross J hat is equal to K hat, and etc. etc. And then you use it, circular permutation. Okay. There are many ways to get the Cos product as you did in Physics 101. Great. Now, let me show you this. So this is what we did here, okay? We use this circular permutation, and then we got it. So magnitude of Q is just FB divided by magnitude of V cos B, as we said. Is magnitude of FB divided by magnitude of V cos B. So V cos B, we can get it easily by doing this. Okay, which is this. And this is what we got before, by the way. Okay. Next, we have an electron at point A here, okay, negatively charged particle electron. And it has this speed, 1.4 10 to the power 6. So the question is, find the magnitude and the direction of the magnetic field that will cause the electron to follow the semicircular path. And I give you the diameter here, which is 0.1 meters from A to B. So what should be the direction of the magnetic field here? Let's look at the direction first, and then we look at the magnitude of the magnetic field. Well, first, the electron is negatively charged, as you see. Of course, we know that the charge of the electron is minus E, minus 1.6, 10 to the power minus 19 coulomb. So the velocity of the electron is up here in the positive y direction. Okay, this is the velocity. Now, what's the direction of the magnetic force? Of course, the direction of the magnetic force is this. So this is FB. And you know that FB is charge of the electron V cos B. In other words, FB is minus E V cos B. Now the question is, what should be the direction of B? So I know the velocity. I know the Lorentz force. Now the question is, what should be the direction of the magnetic field that gives me this FB pointing towards B? You use the right-hand rule, and you will see that the B should be into the page. Okay. Okay, use the right hand rule. So you will see that B should be into the page. Why? Because it's negatively charged. If it was positively charged, the FB, will be opposite. Okay. So B should be into the page. I hope everyone is convinced. Use the right hand rule and you will see that B should be into the page because the charge is negative. Okay. Another way to look at it is to just say that, of course, B is 1 minus E. Minus 1 divided by E. So how do I get it here? So B, it will be FB cos V. So let's get FB cos V. And then we take the opposite direction, the opposite. Okay. So FB is here. V is up. So FB cos V is pointing out of the page. That means B, so FB cos V, this is out, outward. So that means minus outward is inward. So V is inward. Okay, that's just the direction. So be careful, okay? So if it's positive, the FB is in the same direction as V cos B. Okay. Is in the same direction. If it's negative, you take the opposite direction. I'm talking about the charge. If the charge is negative, you take the opposite direction of V cos B. So here B is inside, into the page. Now how to get the magnitude? Easy. So I know that the magnetic force here will play the role of my centripetal force. So the magnetic force has a magnitude EVB sine the angle between V and B. So here sine 90 degrees, which is 1. So I just have EVB. And this should be equal to the centripetal force, which is mv squared over r. So using this, I know what is V and what is R. So V is equal to what? So you simplify here. Okay, so V will be EBR divided by M. In other words, as we said already, R is just MV divided by EB. This is what we demonstrated in class. Okay. So here I know the radius. Of course, the radius is just half the diameter, basically half of 0.1. And I know everything. I know the mass of the electron. I know the velocity in magnitude. I know the charge. So my only unknown is the magnetic field. So the magnetic field will be mass of the electron multiplied by the magnitude of the velocity, the speed, divided by the charge of the electron in magnitude, divided by half of the diameter. And of course, this gives me this. So in Gauss, this is 1.6 Gauss. Okay. You know that 10 to the power minus 4 Tesla is 1 Gauss, right? Great. Okay, let's solve this problem here. Read the problem very carefully. So figure 8 shows a loop of a wire carrying a current, and I give you the intensity of the current, 2 amps, in the shape of a right triangle with 2 equal sides, each 15 centimeters long. So this side 1 has a length L1, and this side 2 has a length L2. And of course, L1 is equal to L2 is equal to 0.15 meters. A uniform magnetic field B of magnitude 0.7 Tesla is in the plane of the triangle and is perpendicular to the hypotenuses. Okay, so As you see, L1 is equal to L2, okay? So that means this angle here is 45 degrees, and this angle here is 45 degrees. Okay? And of course, this is 90 degrees because it's a right angle. Okay, great. Now the magnetic field is normal to the hypotenuses, as you can see. Okay? So the magnetic field is normal to the hypotenuses. So basically, magnetic field is normal here. And it's normal here. Same magnitude, same direction. Of course, normal here. Of course, the magnetic field is normal here. And normal everywhere else, let's say here. Here. Okay, same magnitude, same direction, B. And B is 0.7 Tesla. Now, what's the question? The resultant magnetic force on the two equal sides has a magnitude of. So basically, I want the resultant F, which is F1 plus F2. Okay. So I want to get the magnetic force on the first part, which is 1 here. By the way, this is L1 vector. And then I want to get the magnetic force on the second equal side. Okay, and this is L2 vector. Now let me get FB1. What is FB1? I L1 cross B. So first, let's get the direction. What do you think? Where is the direction of FB1? Right-hand rule. Okay. So direction of FB1 is, of course, inward. FB1 inward. So it's inward. So it's pointing inside the page. What about FB2? The direction of FB2 is also inward. Use the right-hand rule. Okay. FB2 inward. So FB will be inward. Okay. Because it's just FB1 and FB2. So it will be inward. FB will be FB1 plus FB2. And of course, it will be inward. Now, what is FB1 in magnitude? It's just I L1 B sine the angle between L1 and B. So what is the sine between L1 and B? Okay. So here is L1. Okay, it's going the whole way. Here is B. By the way, B is 90 degrees here. So the sine of the angle between L1 and B is this big angle here. So what is this big angle? Of course, it's 45 plus 90 degrees. So FB1 is just I L1 B sine 135 degrees. What about FB2? FB2 is also inward. Okay, is I L2 cross B. If you use the right-hand rule, you see that it's inward. Okay, inside the page. It's getting in. Now in magnitude, FB2 is I L2 B sine the angle between L2 and B. L2 is this, and B is this. So the angle here is 45 degrees. So sine 45 degrees. So that means the net force acting on the two equal sides is just EI, the current L, because actually L1 is equal to L2 is equal to L. B, now here I will have sine 135 degree plus sine 45 degree. So let me put the numbers. I is 2 amps, L is 0.15 meters, B is 0.7 Tesla, and then you put your sine 135 degree, you calculate it, plus sine 45 degree. And of course, this gives you 0.3 Newton. Okay, this is it. Okay, let me just, okay, so that's the resultant magnetic force acting on the two equal sides. Now, what do you think? What about the magnetic force acting on the hypotenuses? Let me call it FB3. Of course, it will be I L3 cos B. Okay. I L3 cos B. So in magnitude, it will give me FB3. In direction, I know that it's inward, right? Is it inward or outward? What do you think? So it will be, of course, inward. Okay. That's the direction inward. Now, in magnitude, it will be I, LB, L3, B, sine the angle between I and L3 and B. Of course, it's 90 degrees. So sine 90 degrees is 1. Okay, so this is it. Okay, and then you calculate the magnitude, of course, yeah. But here I just wanted F1 plus F2. I did not talk about F3. Okay. Now, let me ask you a question now. So, what is a torque acting on this loop? So as you know, torque is magnetic moment cos B. Now, what is the magnetic dipole moment? What will be the direction first? Of course, the direction will be inward. Okay? If I use the right-hand rule, the N here is inward. Okay? So N is pointing inward. Of course, that means my magnetic dipole moment is pointing inward. So I will have N I area multiplied by N cos B. Okay? So you can calculate what's the magnetic dipole moment here. And you will see that, of course, the magnetic dipole moment and the torque is maximum here. Okay, because here you have the torque is normal. So let's calculate the torque here. You will see that, of course, here, this is it. So the torque is here. So you will have, okay, so let me get the magnitude of the torque. It will be NIA NB. So what is the magnitude of NB? The magnitude of N multiplied by magnitude of B. Magnitude of N is 1. Magnitude of B, I know is 0.7 Tesla. Sine the angle between them. What's the angle between N and B? 90 degrees, so sine 1. So you see that the torque will be just N, which is 1, I, which is, I know the current, area, I know the current of this, I know the area of the triangle. So I can calculate the torque, and you will see that the torque is maximum. Okay. The torque is maximum. What about the energy? The orientation energy here, just minus mu dot B. So it's just minus mu B cosine the angle between mu and B, which is 90 degrees. So the energy is 0. Okay. So, of course, this torque here is max. He wants to align the magnetic dipole moment with the magnetic moment. Okay. Good. So I can ask you different questions about this. Okay? And what's the work required to go from basically this orientation to another angle orientation. Okay, so you just say that the work applied or the work required is just plus delta U. Okay, which is U final minus U initial. Okay, good. Anyway, now let's solve this problem. We already solved this type of problem here. Okay, but let me come back to it. So here I have a long wire carrying a current 4 amp. So this is my current 4 amp. Makes two 90-degree bends in the XY plane. So here I'm in XY. Of course, Z is pointing towards U. And it's placed in a uniform magnetic field here. As you can see, the uniform magnetic field has a magnitude 0.25 Tesla along the negative Y directions. You see the magnetic field is pointing downward along the negative Y direction. So including the bend part, the total length is 20 centimeters. Okay, so here I have 8 centimeters plus 4 centimeters, 12 plus 8, so 20. So 20 centimeters is the total length of the wire. Okay, great. Now find the magnitude of the net force that the magnetic field exerts on the wire. Okay, great. So I want FB. How do I get FB? IL cos B. Okay. Now, as I said in class, it's I. This L here has two components. The L parallel to B plus the L perpendicular to B, cos B. Of course, the L parallel to B does not do anything. Okay, so here this is just I, L perpendicular cos B. Okay, so what is the L parallel to B? This is the L parallel to B. So here the magnetic force is 0. Okay, there is basically, you know, the IL. Okay, this 4 centimeters here, there is no magnetic force on it. Why? Because L vector, which I call here L parallel to B, of course it's parallel to B, so L parallel cos B is 0. So no magnetic force here. So the magnetic force here will act on this L perpendicular. So this is perpendicular to B and this is perpendicular to B. So these two portions here of 8 centimeters will feel the magnetic force. Okay, so that's the L which I care about. So here I will have FB, just I, L perpendicular cos B. So in magnitude, FB is I, L perpendicular, B sine 90 degree, which is 1, of course, because between the B and the L perpendicular, of course, you have 90 degree. So basically, I just have I, L perpendicular B. So I is 4 amp. L, what's L? Well, L is a total length, perpendicular length. So 8 plus 8, so 16 centimeters. So you put it in meters, 0.16 meters times B. And B is 0.25, of course. Okay. And this, we already discussed this in class. So this is the net force. Next. Let's read this question very carefully. It's a conceptual question and we solve it. So we have here 3 rectangular coils of the same cross-sectional area that are placed in a uniform horizontal magnetic field B, as shown in the figure. All the coil carry the same current I. Rank the situation according to the magnitude of the torque on the coil, greatest first. You know that torque is just mu cross B. So it's just number of turns. Here number of turns is N. So here N is equal to 1, I, A, N cos B. Okay. Now let's look at the first one. Of course, if I use the right-hand rule, what's the direction of my N? course, n is going in this direction. So this is the direction of the normal vector. Okay? And of course, it's the direction of mu. Okay? So here, what's the direction? It's a little bit tilted, so you have a certain angle. Okay? So the direction is somewhere like this, let's say. So here, what's the direction of the normal vector and of the mu? You use the right-hand rule, you will notice that, of course, the n is inward here. And you have 90 degrees between n and b. So here you have theta is equal to 0, the angle between n and b. Here the angle is between 0 and 90 degrees, and here the angle theta is 90 degrees. Now let's get the magnitude. Magnitude is just magnitude of torque is magnitude of mu, magnitude of b, sine the angle between them, which is theta. Of course, the theta is max, sine theta is max when theta is 90 degrees. So 3 is the largest. Okay. Then of course 2, and then of course this theta is 0 gives you the smallest torque. Okay. So of course this is my answer. Okay. So is it clear? Great. So n mu is going in the same direction as n. So it's just n. Mu is in this direction as well. And mu here is in this direction as well. Great. Now, if the question was rank the situation according to the orientation energy. Okay. Greatest first or most positive first. What do you think? So same question, but now the question is rank the situation according to the orientation energy. You know that the orientation energy is just minus mu dot b. The torque is mu cos b. The orientation energy is minus mu dot b. Okay. So it's just minus mu b cosine theta. So can you rank them according to the orientation energy? Most positive first. Of course, this guy will not be the most, this guy will be the most negative, right? Just minus mu b, this guy here. Okay. So what is this? So what do you think? Here you will have a u which is 0 because the angle is 90 degrees. So the torque is max. Okay, but the angle is 90 degrees, so u is 0. And here you will have here what? Basically in the middle. Okay. So it will be 3, that's 0. Then this one, 2, then 1. Okay. Right. Now this problem, I will let you solve it. The solution is given. But it's a very interesting problem, okay? This problem, we already solved it. We already solved this problem. Okay, this is also kind of straightforward. Yes, now this problem is what I want you to finish by. So read the problem carefully. I give you the charge of the particle, which is this. And I give you this. It moves through a uniform magnetic field, but I did not give you B. Okay. I gave you the velocity. So this is the velocity. And I gave you the magnetic force. So basically here, FB is QV cos B. I give you this. I give you this. Now I'm asking you what is B. But here I said if the X and Y component of B are equal, find B. Okay, so the X and Y components of B are equal. Okay, so B will be, let me call it along X, B naught, along Y, B naught, and along Z, I will just have BZ. Okay. So along X and Y, they are the same. Now the question is, knowing FB and knowing V, find me B. That's it. So this is what we do. Okay, here I just call it B1, B1, B2. I said B1, B1, B2. So B1, B1, B2. And you use, you know, everything. The only unknown is this B. Okay. Another way to get B is to say that, well, B will be what? 1 divided by Q, because I know Q as well. It's 3 Coulomb. 1 divided by Q, F cross V. So I know F, I had J hat, K hat. So what should F be? F is just 36, 24, minus 12. And what is the next one here, which is V? V is just 2, 6, 0. Now what should be B? So you calculate B. Great. Anyway, so let's stop here. I want you to solve this problem. This problem is also straightforward. Okay, you can calculate it easily. This we already solved it. This is also straightforward. Let's look at this one if you want. Okay, but it's also straightforward. I think you can solve it easily. Okay, this chapter is not difficult, but solve all the recitation problems, inshallah, and you are good for the exam. Okay, so be ready. Okay, I don't want anybody to be caught surprised. So be ready for the exam. Okay, do your best, and inshallah you will not have regrets. Assalamu alaikum.